Okay, problem 833. Show that for a degrees of freedom nu very large, larger than 2, then the variance of this t nu is equal to this. Okay, so to show this, we actually need to think about the original distribution of t nu and use that to figure out the variance. Okay, so the original distribution, the PDF of t, is given by this. That's what we learned from the class. Now, on the one hand, we know that the expectation of t is equal to 0 because the shape this is actually an even function about 0. So the expectation of this is just 0. It's symmetric. The curve is actually symmetric about the y-axis. Okay, so that's why expectation is 0. So the variance is nothing but just the second moment. Okay, so we just need to compute this. To compute this, we figured out just by definition, expectation of t squared is just the integral of the t squared and multiplied by the PDF. And because the shape of this again is symmetric about t, okay, unless it's an even function of t, so it's just a double of the integral of this from 0 to positive infinity instead of this. But we need the 2 here. All right, so now we just plug in the formula here to this f, then we try to compute it. Okay, after multiplication, then we can do a change of variable. So this is the integral we're trying to compute, or more especially, this is the integrand. So to compute this is not very trivial. We're going to do a change of variable. First, we multiply this. We call this 1 over u. Okay, by doing that, we can see that the t squared, so we can try to solve for t squared, we see that t squared is this. Okay, just subtract both sides by 1 and multiply both sides by nu. So we get this, and then taking the square root, we'll get this. Okay, so from here, we can see that the dt du is just taking the derivative with respect to u here. So we'll get this. Okay, we'll get this. Now from here, we can do the integration because remember that previously we have this as the integral we're trying to find. Right now, this is replaced by the 1 over u, and this t squared is replaced by that, and also this dt should be replaced by dt du times du, but dt du is this. So that's how we get these 3 terms. Okay, that's how we got this. So this constant never changes; it's still outside of the integral. And on the other hand, remember that when t goes from 0 to positive infinity, this thing goes from 0 to positive infinity. So the whole thing goes from 1 to positive infinity, and that means u is going from 0 to 1. Okay, or actually 1 to 0 as t goes from 0 to positive infinity. That's why we change the limit as well. That's how we do the change of variable. That's what I learned from calculus. And now the rest is just doing some simplifications, and then after very simple simplification, we get this. Now from here we do not really compute it. The key here is that you can recognize this, especially this part is something familiar to us because this is the somehow like the beta distribution. Remember that for beta distribution, if we have an integrand or we have PDF proportional to this, alpha minus 1. So I should say u to the alpha minus 1 and 1 minus u to the beta minus 1. If you have a PDF proportional to this, then your random variable u will be following the beta distribution with alpha and beta as the degrees, as the parameters. So now we just treat this as alpha minus 1 and this as a beta minus 1. Okay, then from here we can see that beta should be 3 halves, and alpha should be, say this is minus 2, so alpha should be nu minus 2 over 2. Okay, so that's alpha, that's the beta. So from here we can directly pull out this, and then integral of this thing should be just the constant in front of the PDF of the beta distribution, which is gamma of alpha plus beta, that is this, and then gamma of alpha, then gamma of beta. Okay, so now we just do this, and then after this step, to simplify this whole thing, the key is to get rid of those gamma distributions or gamma functions, sorry. So for example, here this can be cancelled. Apparently this can be cancelled. This and this are not all the same, but they can be cancelled as well. The reason is a gamma distribution, the gamma function has a very elegant property. For any positive alpha, the gamma of alpha plus 1 is equal to alpha times gamma alpha. So that's why here this is just 1/2 times the gamma of 1/2. Okay, because you can treat this 3/2 as 1/2 plus 1. So then you just use this. So you have this replaced with this. Okay, and similarly, you can see here the difference between these two. This is just essentially half of nu minus 1. So essentially, this just this and this can be simplified into just this part, because this times this together is this. Okay, again, I'm following this property where here we just set alpha to be nu minus 2 over 2. That is actually one requirement we had earlier. We need this nu minus 2 to be greater than 0. Okay, so that's how we got that. And then you can cancel this. Oh, by the way, sorry, this should be equal to this, the product of these two. So that's why we can cancel this, and only this part is left. And also the gamma of 1/2 is equal to square root of pi. So that is why they cancel with square root of pi here, and then after certain simplifications, we get that. Okay, so that is why the variance of the t random variable, sorry, it should not be t squared, it's just t. The variance of t, which is just this, because the expectation of t is 0. The variance of t is just the nu over nu minus 2. Okay. By the way, you can see that when nu is getting larger and larger, this variance is almost equal to 0. Almost equal to 1, right? So that is also a verification that when the degrees of freedom nu is very large, the t random variable is approximately just the standard normal random variable.